this video, we solve problem 2.6.27 from Nagle's Fundamentals of Differential Equations 7th edition. We're asked to use the method for solving Bernoulli differential equations to solve the following differential equation. And we have r as a function of theta, and dr d theta is equal to this quotient. Now on the surface, it may not be obvious that this is a Bernoulli equation, but if we do a little bit of algebraic manipulation, it becomes more obvious. Since I have a monomial in the denominator, I can take each of these terms in the numerator and just divide them by that monomial. So I can write this as r to the 4th over 3 times theta to the 5th plus 15r times theta to the 4th over 3 times theta to the 5th. Now 4 of those thetas here will reduce. So we'll just have the 1 theta in the denominator. 3 goes into 15 5 times, and we could rewrite this as well. So notice that the dependent variable is r. And so what I want when I write this differential equation in what we've been calling standard form is dr d theta plus a function of theta times r equals a function of theta. I know the variables are different, but r is playing the role that y typically plays, and theta is playing the role that x or t typically plays. So I'm trying to make this equation look like this. Well, there's an r right there, an r to the 1st. So if I subtract this from both sides and sort of factor out the r, what I end up with is this, dr d theta minus theta, or 5 divided by theta times r, is equal to this expression. Ups, and this is for a Bernoulli equation, we should have an r to the n on the far right with n not equal to 0 or 1. So I want to write this as a function of theta times r to the 4th in this case. So I'd factor out that 1/3. I'd write that as a theta to the negative 5th. And then I've got an r to the 4th right there. So this is Bernoulli. It has that form with n equals 4. Okay, so let's solve our Bernoulli equation. When we solve a Bernoulli differential equation, we always start by letting u equal our dependent variable. In this case, that's r, to the 1 minus n power, and n in this case is 4. Don't let the change of variables bother you. You just have to remember what is the dependent variable and what is the independent variable. So we're going to let u equal the dependent variable to the 1 minus n, and then you want to compute du d theta, where you remember that r is a function of theta. So u is r to the 1 minus 4, which is r to the negative 3. That means du d theta, by the chain rule, is negative 3 r to the negative 4 times the derivative of the inside. That's dr d theta. So then we're going to take this differential equation in standard form, and we're going to multiply it by this coefficient here. I'll call this this differential equation dE star. So you have dE star times negative 3 r to the negative 4. So you have negative 3 r to the negative 4 times negative 5 over theta. So negative times negative is going to give us a positive. 5 over theta times r equals 1 over 3 times theta to the negative 5th times r to the 4th times this expression, negative 3 r to the negative 4. And by design, these reduce. The 3's also happen to reduce, and we end up with a negative 1 times a theta to the negative 5 on the right-hand side. By design, this whole piece is du d theta. Those are the same thing. So I can replace this with du d theta. And then here I've got 3 times 5, which is 15, divided by theta. And r to the negative 4 times r to the 1st is r to the negative 3rd, and r to the negative 3rd is u. And we end up with this. So we let u equal that, we compute du d theta, and then we multiply the differential equation by this 1 minus n r, well, I wrote y, but r to the negative n. And then we simplify. And when I say simplify, what I mean is I'm writing the differential equation in terms of u. When we do that, this differential equation will always be first order linear in terms of the new variable u, and it is. We've got the derivative of u with respect to theta plus a function of theta times u equals a function of theta over here. So now we're going to solve this using an integrating factor. So we identify p of theta. That's the 15 over theta. And then we compute its antiderivative. So we get 15 times natural log of the absolute value of theta plus c. We only need one integrating factor, so we're going to choose c to equal 0. That's going to give us a natural log of theta to the 15th, because you can bring that inside. We're just using this fact from algebra. And then we want to define the integrating factor to be e to this power. You can use mu if you want to, you don't have to. And I made the mistake of writing it as a function of x. It should be a function of theta. There we go. So our integrating factor is e to this power. The exponential and logarithmic functions undo each other, so we get this, as long as theta is non-zero. So let's just assume that theta is positive, and then we'll have theta to the 15th. If theta was negative, we'd have -1 times theta to the 15th, and that would be fine. So I'm going to call this equation involving u and theta, our first order linear equation in the variable u, dE double star. And to solve that, we're going to multiply by this integrating factor, theta to the 15th on both sides. When we're done, the left-hand side should be the derivative of u times our integrating factor. So let's actually do that and see if we get the right thing. So our differential equation was du d theta plus 15 over theta times u equals theta to the -5. And we're taking all of these terms and multiplying them by theta to the 15th. And then after simplifying, we get theta to the 15th times du d theta. And one of these will reduce with one of those. So we'll have 15 theta to the 14th times u equals this product. The bases are the same. You just add the exponents, and we're there. Okay, now at this point, the left-hand side should be the derivative with respect to your independent variable, in this case, theta, of the dependent variable for the differential equation, which was u, times the integrating factor. So if we've done everything correctly, the left-hand side should be the derivative with respect to theta of u times the integrating factor, which is theta to the 15th. The question is it? We can always check using the product rule. Remember, this is operator notation. This is not a product. this is the derivative with respect to theta of this product. This is a function of theta times a function of theta. So if I were to take the derivative of this using the product rule, I would get derivative of the first, which is the du d theta, times the second, that's there, plus the derivative of the second, which is the 15 theta to the 14th, times the first. And it checks out because we just use the power rule for that derivative there. So now we're just 2 steps away from getting u by itself. Want to get rid of differentiation with anti-differentiation. So we're just undoing operations. And so we get u times theta to the 15th is the antiderivative of theta to the 10th. So you'd add 1 to the exponent, divide by the new exponent. Don't forget to add a constant of integration. And then in order to get u by itself, we'll divide both sides by theta to the 15th. And if you want, you can divide each term by theta to the 15th. It's really up to you. And now we have u as a function of theta, and that is 1 over 11. And we end up with 11 of these reducing. You still have 4 thetas in the denominator, plus c over theta to the 15th here. Okay, great. And now that we have u, we're still not done. We have to solve the original problem. Remember, our original problem was about r. It's been a little while, but we're trying to get r as a function of theta. So we have to remember what r was in terms of, or what u was in terms of r. U is actually r to the -3. So this u of theta is actually r to the -3. And actually, given that this is a negative exponent, it would have been helpful to write that with a single denominator. So I think what I'll do is I will multiply this by theta to the 11th over theta to the 11th to sort of get us where we were before. And then let's multiply this one by 11 over 11. So we have theta to the 11th plus 11 times c is just a different c over 11 times theta to the 15th. Now that I have a common denominator, and I'm trying to get r by itself. So I'll raise both sides to the -1/3 power. You're just going to raise both sides to the reciprocal power to isolate r. And when we do that, we end up with this. R of theta on the left-hand side equals this to the -1/3 power, or you can flip it and raise it to the 1/3. That's the same thing. And that's probably how I would write it. Now, of course, theta to the 11th plus c2 is not allowed to equal 0, and we already said that theta was strictly positive. So we would want an interval where theta is strictly positive and this denominator is non-zero. Now, the value of c would depend on some initial condition, but we weren't given one in this case. So I would just stop here. Now, if you're entering your answer in MyLab math, rather than calling this c sub 2, you might just call it c. Just keep in mind that c is different from that c, that's all. But that's the solution to that problem. So just as a brief review, we started here, and the first thing we did was we wrote it in this form. We noticed that r was our independent dependent variable, theta was our independent variable, and we're trying to make it look like this. So through some algebraic manipulation, just dividing each term by the monomial, and then rearranging the equation, we got here. And then after we did that, we said, okay, now we've got our Bernoulli equation in standard form where n is equal to 4. Let's let u equal the dependent variable, which is r, to the 1 minus n, compute u d theta, figure out what that coefficient is, and you're going to multiply that expression by every term in your differential equation in standard form. When you do, the resulting differential equation will be first order linear in the variable u. So you solve that with an integrating factor. And we remember how that works. And then once you figure out what u is, then you back substitute r to the -3 in this case. You raise both sides to the reciprocal power to get r by itself. And you simplify a little bit if you can.